Hi everyone, this is Daniel from Tensor Data Scientists. As promised, I want to show you how you can compute multiple linear regression from scratch using Python without the standard libraries like scikit-learn or stats models at API. And I'll show you how to actually compute pretty much every single metric in your stats models at API summary output for multiple linear regression, both in Python using just numpy and scipy, as well as in Excel or in Google Sheets or spreadsheet using just built-in formulas, no plugins, no add-ons. AI is all the rage right now. This is kind of a foundational thing, not really this is not large language models, not an LLM. This is not neural networks, but all neural networks, which is what LLMs are based on multiple linear regression, right? That's basically they're just layers and layers and layers of multiple linear regression with nonlinear activations. So it's really good to understand this stuff very, very well. So if I think it's worth going through this just so you can learn how this all works mathematically. Although I should say that what we're doing here is OLS, ordinary least squares, which is solvable mathematically. The way that linear regressions or the way that neural networks typically solve linear regressions is not with OLS. What they do is an iterative method called gradient descent primarily, which we're not going to get into. But I think it's still really helpful to go through this just so you could have a intuitive understanding of what we're doing and why. So I'm not going to go through the entire notebook here or everything that we do in the Excel spreadsheet because this notebook really explains it very, very well. I might also create a Medium article on this, which you can read at your leisure, and I'll put links to everything below in below the video. But I do want to show you the key piece. Okay, so the key piece is where we compute the coefficients themselves for linear regression. So let's just take a quick look at the math behind that. So in linear regression, we're assuming that y, a vector of values, which is often referred to as the target in machine learning or the output in statistics, might be referred to as the endogenous variable or the dependent variable, right, is a function, a linear function of x, which is a matrix because it's multiple linear regression here, so we have multiple columns of x. So it's a matrix of x which has the same number of rows as there are elements of y, but it could have some number of columns. So we'll call it has p columns and n rows, and y is an n-length vector, right? So this matrix times beta, which is a vector of coefficients that has the same number of elements as the columns in X. So we transpose that for linear algebra reasons. So it's y is a function of this X matrix times the beta transpose plus some error. And we're assuming that that error is a normally distributed random variable with a mean of 0 and some unknown variance sigma squared. Now, you might be wondering, okay, well, where's that constant? Where's that intercept, right? That, if in many versions of learning about linear regression, you might have remembered that there is a beta 0, right? Which represents the intercept where the line in simple linear regression or the hyperplane in multiple linear regression intersects the y-axis. And the answer is it's still here. We're just kind of hiding it. So what we're doing is here, the beta 1 through p is multiplied by a column of x, and beta 0 is not. So what we're going to do is we're going to add a column of x, which we'll call the constant column, and it's just going to be ones, just going to be n ones. So beta 0 times 1 is obviously still beta 0, so that allows us to do this math much more conveniently. So let's get into a little bit of the code and the Excel. And as I said, we're not going to go through everything, but just the really key important things. So you can go through this slowly on your own, but we'll use these libraries. We import this data set from stats models, which is just some macroeconomic numbers. And we're going to select 7 of those columns as our x variable, and we're going to use those to predict, and notice that we add a column here constant, so that's our 8th column, or we'll make it our first, but now there are 8 columns with our constant, which is just 1. And we use those to predict our y, which is going to be the unemployment column. So we're going to use these 7 variables plus an intercept to predict y. And if you wanted to do this and you're following along, you can run this line right here, which copies it to your clipboard, and you can just paste it right into Excel. So let's take a look at the output from stats models. So when you just run OLS, ordinary least squares, we're trying to predict y using x. and we look at the output of the fitted regression. We have the first table here, which is a bunch of metrics associated with the overall regression. Then we have the second table, which are the metrics associated with each individual coefficient for each column of X, or each variable, or each feature. And then you have the third table, which is mostly metrics associated with the error and whether or not the error is truly normally distributed, as well as another number here that's associated with intercollinearity of the variables. The Durbin-Watson here actually measures whether or not your error is homoscedastic, which means that it has constant variance. So we're going to show you how to compute every single thing in this on these three tables from scratch in Python, in Jupyter Notebook using Python, as well as almost every single thing here, with the exception of this condition number, which we can't really do in Excel, right? Using just Excel with just built-in formulas. Won't go through everything in this video, but I'll show you the really key important thing, and that is predicting. Oh, well, actually, one thing before I show you that is, if you take a look at these values right here, they're rounded to, here it's rounded to 4 decimal places, and here it's 3. That's pretty imprecise. It's in the back end, it's actually stored at a much higher degree of precision. So we actually go through each and every one of those metrics and save them in their higher precision form so we could do a better comparison to our own computations with that. And what we'll see is that not everything is exactly the same, but they're really, really, really close. So let's hop down to just computing the beta coefficient estimates. So the beta coefficient estimate is often referred to as B, or beta hat. And this is the math. It's that simple, right? I know it maybe looks a little bit funny, but bear with me. Inside the parentheses right here is the matrix multiplication of X transposed times X. So an X transpose are just basically flipping the rows and columns of X. So X is our matrix of features. It has n rows and p columns. So when you flip it, it now has p rows and n columns. So you take a p by n matrix, and you multiply that by an n by p matrix. You end up with a p by p square matrix. We then invert that. So we take the inverse of that matrix, which is, in scalar terms, that's akin to taking a reciprocal. And then, so now we have, it still stays a p by p matrix. It's just now the inverse form. And then we multiply this p by p matrix by by X transpose again. So it's now by a p by n matrix. And so we end up with a p by n matrix right here. So that's and then this multiplied by y, which is just an n length vector. So you can think about that as an n by 1 matrix. So now you have a p by n matrix times an n by 1 matrix, and you end up with a p by 1 matrix, which is exactly what we're looking for. And these are our coefficients. Okay. Now in Python, really easy to do, right? You could use the np.linalg.inv function to invert a matrix. And you can use the at operator, which does matrix multiplication. There are other ways to do it, but this is really clean and easy. And then the .t method on any matrix transposes it. So really easy to write this out in Python. One line, and you've got your beta coefficients. You don't need to use stats models. You don't need to use sklearn. It's really easy with just numpy. All you need is numpy for this, right? And if you didn't have to invert it, you wouldn't even need numpy. But I'm not going to write the inversion algorithm from scratch here. By throwing on our index, we can then see the names here, so that's helpful. But this is literally all you need right there. That's that single line. Now let's hop over to Excel. Now I did this in Google Sheets. I also saved an Excel version. It's exactly the same in both. So just take a quick look. This is the original output that I pasted from stats models, but it was not precise enough to have good comparisons. So then I individually pasted all of these, which are much more precise, which I pulled out of stats models. And then these right here are all the Excel-based versions. So let's take a look at our coefficients. So what we have here is the xtxi, right, which is, if you remember from over here, this is just this. I'm calling this xtxi, and I'll show you how I created that soon. And I'm using the mmult function in Excel, which is matrix multiplication, to multiply that by this, right? And this is the mmult, which is the transpose of x, and multiplied by y, which is that right here. So this multiplied by this creates our coefficient. Oops. Now this, error, Control Z. So this right here is an array formula. And it's called an array formula because it does matrix math, and it operates in a different way than typical Excel formulas do on multiple cells simultaneously. And it also, the output will take up multiple cells. So this will actually just will actually fill in all the cells below when you do it. Okay. Let's head over to, actually the right way to do this would be to select them all when you put in the formula. You put in the formula, hit enter, and it'll all kind of fill in. Let's head over to the XTXI piece. So just before you do that, our X matrix is pasted in here, and I named the range X. Okay, that makes it much easier to use by naming the whole range X. So if this were Excel, you would actually see it says X over here. I think if I wanted to show you the named ranges, right, we could go to X over here. So it's A14 through H216. As you can see, that's A14 through through H, there we go, H216. Okay, so that is our X, and we go into XTXI over here, and simply what I showed you before, right? We take the transpose of X, which is an array formula. We do the M mult of the transpose of X times X, and then we take the M inverse or matrix inverse of that, and that gets us this right here. And this is what we use to compute the coefficients. Now, everything else here, you can follow the formulas if you want to figure out how it's done. If you have any questions, feel free to reach out and ask me, and enjoy.